It would be really nice if we could look at a square matrix and compute a single quantity that would allow us to determine whether or not that matrix has an inverse. Now remember, we're only dealing with square matrices when we're talking about inverses, and as a result, this statement will only apply to a square matrix. So we actually have this quantity called a determinant, which, to help you remember that, it determines whether or not A has an inverse. Okay, so moreover, the value of having an inverse is then if it's associated with a system, if that coefficient matrix applies to some system, AX equals B, well, we know we could solve this with Gaussian elimination each and every time, but if we have an inverse, then we can multiply both sides by that inverse, and we get the identity matrix here, and we get identity times X, or just X, is A inverse B. Now that's going to yield a single vector of individual quantities, and so if A has an inverse, then the system will have exactly one solution. If it does not have an inverse, then we don't know. It could be that there's no solution or infinitely many solutions. So let's try to unpack and figure out how we would find this quantity called the determinant. How do we formulate this metric that will tell us whether or not we should even bother looking for an inverse? So let's just take a look at the 2x2 system. AX plus BY equals C1, CX plus DY equals C2. So X and Y are the variables, A, B, C, and D are the coefficients, and C1 and C2 are the constants. So we know that in 2 dimensions, these lines will have one solution if they intersect exactly once. Well, how do we know if they intersect exactly once? What quantity will tell us this? Well, the key is they have to have different slopes. Different slopes. Okay? As long as they have different slopes, well, then that means they're going to intersect somewhere, right? Even if they don't intersect right away, they will eventually cross, and that counts as a solution to the system. So let's start off and just get these into slope-intercept form. So AX plus BY, if I subtract AX over, so C1 minus AX, and then I divide by B, okay, so I'm going to divide by B, so I'll divide this by B, I'll divide this by B, and I could write that a little bit more neatly in slope-intercept form as negative A over B times X plus C1 over B. Now keep in mind that A, B, C, and D could themselves be positive or negative numbers. C1 and C2 could be positive or negative. So this doesn't necessarily mean this has a negative slope, because if A is negative, then we end up with and B is positive, then we end up with a negative negative, which is a positive. And similarly for the second equation, subtract CX from both sides. So C2 minus CX, and then divide both sides by D. And then rewrite it a little bit more neatly. Y equals negative C over D times X plus C2 over D. Okay, now what we know from slope-intercept form is here, if we think about this as mx plus b, well, here are our slopes and intercepts. So we have slope, we have y-intercept. Now we don't really care about the y-intercepts, all we really care about is the slope. We're saying that they'll intersect exactly once if they have different slopes. So let me do this. This will make for a nice equation. We will write that the slope of equation 1 has to be different than the slope of equation 2. So here's the slope of equation 1, that's this guy here. Negative c over d is the slope of equation 2, and for them to be different, that means they are not equal to one another. Not equal to. Now you might not be used to working with not equal signs. You could put an equal sign there and say, well, if they are equal, they'll either be the same line or they'll be parallel lines not touching, leading to no or infinitely many solutions. But you can work with a not equal sign in the same way that you do with an equal sign. So let me manipulate this around a little bit. First of all, I'm going to cancel out the negatives. Just make this a over b can't be c over d. And then I'm going to multiply both sides by b and multiply both sides by d. So I'll multiply by b, multiply by b. That'll cancel these b's out, and then I'll also multiply by d on both sides, just so I get rid of the fractions. And so I'll have d times a, or a times d, cannot be equal to b times c, or c times b. Now if I move that over, and I get this expression, or this inequality, AD minus BC is not equal to 0. So for them to have different slopes, for different slopes, AD minus BC cannot be equal to 0. Okay, so that will mean A inverse exists, and it will mean that if there's a system associated with this matrix, the system has a unique solution. It has exactly one solution. The lines intersect exactly once. And to illustrate this, here I actually have those two systems in here. AX plus BY equals C1, CX plus DY equals C2. I have all these sliders in there that will actually allow me to manipulate this. So if I change A, you can see I get rotation. If I change B, I get a different kind of rotation. C just moves the y-intercept. C1 moves the y-intercept. And you can see that if I look at now AD, or negative A divided by B, and I look at negative C divided by D, okay, those are our actual slopes of our lines. The red line has a positive slope of 1.22. The purple line has a negative slope of negative 0.2. And let's see what happens when these become equal. Let's see if I can get them to be equal. Okay, I can't do it with that one. Let's try it with changing C. Oh, look at that. Almost equal. Now, I can't get it exactly equal, but you see that if A, B, and C, D are, A over B and C over D are equal, this is very, very close, you can see that they will be parallel lines. And so that will mean, well, in this case, there's no solution if the slopes are the same. But if I change the y-intercept a bit, come back here and make this, there we go, we'll leave it at that. If I change the y-intercept, then you can see, oh, now they can have infinitely many solutions. So just by looking at the slopes, if they are equal, you just know that they're either the same line or parallel non-touching lines. If there are different slopes, they will intersect exactly once. And that's what we've established here. So there's our quantity that we were talking about. This one quantity, AD minus BC, if it is equal to 0, well, that means the system has either no or infinitely many solutions. That's the same thing as saying A over B is equal to negative C over D. However, if this quantity is not 0, then the slopes are different and A is invertible and the system has exactly one solution. All right, let's restate this in how we might see it in a book. Define the determinant of a square matrix A equals components A, B, C, D to B, and we'll write it like this, determinant det of A is equal to AD minus BC. So when we say det A, we mean the determinant of A. And here are the conditions. If the determinant of A is not 0, then A is invertible and the system has exactly one solution. If the determinant of A is 0, then A is not invertible and the system may have either no or infinitely many solutions. Okay, I say if applicable because we might not actually be solving a system of equations, but the idea of the inverse is what's key there. Det A not 0, A is invertible. Det A equal to 0, A is not invertible for the reasons that we just unpacked up here. Okay, if det A is 0, we just can't tell whether the solution set is 0 or infinitely many. If we come back over here, then we have to take into account the vertical intercept, and that's just too much work at that point. We already know that the inverse doesn't exist, and that's what's important. Okay, so to compute the inverse, the determinant, you just compute AD minus BC and check if it's 0 or not. Simple as that. It's a binary outcome. Now, how do we compute the determinant of a 3 by 3? Oh, and let me just give you a quick example here. Let's say I'll make up an matrix A and let's figure out, let's say 1, 2, 3, 4. Does it have an inverse? Well, I'll compute A times D, which is, notice the product of the diagonals. See that? We have A times D minus B times C, which is the product of those diagonals. Okay, so we'll have the determinant of A is 1 times 4 minus 2 times 3, which is 4 minus 6, which is negative 2. Okay, negative 2 is not equal to 0. So the determinant of A is not equal to 0. Our conclusion is A inverse exists. Didn't find it for us, but it was a quick way just to check whether it will have an inverse or not. Now I could come up with a system where I have like 1, 1, 2, 2, and the determinant of A will be 1 times 2 minus 1 times 2, which is equal to 0, which means that A inverse does not exist for this particular example. Now for 3x3s and bigger square matrices like n by n, 5 by 5, 6 by 6, there's a really messy formula, and it's just kind of frustrating to use, and we often don't do determinants for larger matrices by hand anyway. So I'll just show you how 3x3s work. The logic is this. With planes, though, there are 2 different slopes. If this is a plane, let's think about this as a plane. I have this tilt, and I have this tilt. So there's actually a slope in what we call kind of the x direction, dz dx, and also dz dy, or delta z delta y. And so it's a little bit more complex to derive the formulas, which we aren't going to do here, but I'll show you just kind of an example of how we work with it. So let's say A is this matrix where we call the components A11, A12, A13, A21, A22, A23, A31, A32, A33, where the first subscript denotes what row we're in, and then the second you can see denotes that we're in column 1, column 2, column 3. So the way you compute this is take the first coefficient, which is this one right here, and kind of cross out the row and column in which that value takes place. Then take the determinant of the values that weren't crossed out. So notice that that's the determinant of A22, A23, A32, A33. So take A11, that component, and multiply it by the determinant of what's left when you cross out the corresponding row and columns. Plus, okay, now the second term is going to be a negative. Is going to be a minus. Notice that that's a minus. The other 2 terms are just unsigned, or whatever sign A11 and A13 are. So now take the next value. So we've just shifted over to the next value. Cross out the elements in the same row as A12 and the elements in the same column as A12. And then the values that aren't crossed out, form a matrix out of them. A21, A23, A31, A33, compute the determinant of that. Multiply that by A12, subtract that from the first piece. Finally, move over one more column, and now we've done this value, and now we're going to go A13, cross out the values in the same row as A13, same values in the column as A13, and notice that we have this matrix A21, A22, A31, A32. Compute its determinant, multiply it by the value of A13, and add that to the previous result, and you have your determinant. Okay, so let's actually do this and see how quick it is to compute. Just don't forget about that minus sign in the middle there. So here we go. Start off here. So A11, that value, cross out the column and the row of A11. So 1 times the determinant of this matrix right here. Okay, so that's going to be 5 times 9 minus 6 times 8. We have this minus sign here, and now what we need to do is we need to move over to this value, cross out the elements in the same row, in the same column. 4, 6, 7, 9, compute the determinant of that, so I'll kind of do one of these. 4 times 9, so this can be minus 2 times quantity. 4 times 9 minus 6 times 7. Okay, plus now we're moving to the final column, so now we're going to move to the element 3. Cross out the row, cross out the column. It'll be 3 times the determinant of 4, 5, 7, 8. So 4 times 8 minus 5 times 7. And that's going to come out to, let's see, 1 times, that's 45 minus 48 is negative 3. So it'll be 1 times negative 3 minus 2 times 36. 36 minus 42 is negative 6. Plus 3 times 32 minus 35 is negative 3. And let's just double check. It's 36 minus 42, negative 6. 45 minus 48, negative 3. Okay, so now multiply all this together. So this is the determinant of A. And we get negative 3 plus 12 is 9. 9 minus 9 is 0. Okay, wow, that worked out perfectly, didn't it? So we find out the determinant of A is equal to 0. So A inverse does not exist. You will not be able to find the inverse of this matrix. And also, that means that if this were a coefficient matrix, the system AX has 0 or infinitely many solutions. Now, for larger matrices, we would go and use technology for it. Even the 3x3 is starting to push it a little bit, but I like to show the 3x3 since we see that it actually involves computing 3 2x2 determinants in the process. Now, you can imagine that a 4x4 would require 4 3x3 determinants, which would require 3 2x2 determinants, and it kind of keeps on, it just keeps getting bigger and bigger and bigger from there.